everyone. I am Evan Pheonix. I work as an engineer at work on Rubinius, and I'm going to be talking about Rubinius, but what have you done for me today? It's been a really great year for Rubinius. At last year's RubyConf, we announced that we were finally doing a 1.0 RC of the project, and now we're just about ready to do our sort of third release, bug fix release for the first feature release, 1.1.1. But let's do a real quick, because I don't know what kind of audience necessarily I've got here, so we'll do a real quick sort of like, what is Rubinius, just to get this out of the way. So it's it aims to be a modern Ruby implementation with a specific philosophy of trying to use Ruby to do as much of the work as we can inside the system. So allow Ruby to extend the system. So the quickie example is always this one. So this is not a contrived example. This is actually the copy and paste implementation of map that we use in the system that everybody uses. It's not just some slideware. This is the real deal. This is the only implementation of map that we have. And it looks exactly as you would, if you were to write it, this is probably what you would write. So this is sort of the canonical idea of Rubinius, that the way that you would write it the first time is probably the way that we would write it as well. So we aim for 1.8.7 compatibility, and we'll talk a little more at the end about future things, 1.9 and that kind of things. We run Rails 2.3. We track Rails 3 head, actually, so we try and make sure that we're always going to be compatible with the next version of Rails, so that people don't have that hang. People can always sort of depend on that. A big part of the project has always been to be able to run C extensions. So when we started off, we really hammered it hard to make sure that we can run C extensions so that people didn't have to go through and re-implement all that functionality that they use in terms of Mongo, in terms of all those different things, Mokagiri, that we didn't want to have to redo again, so we wanted to give that power into the system as well. We've had a number of spin-off projects such as RubySpec and FFI, and really the idea is to be drop-in compatible. You could be using Rubinius, and you could stick it right in. You could just drop it right in there, and not have to really change much about what your workflow is. Technology-wise, what does it mean to be a modern Ruby, a modern VM? We try and bring a lot of technological innovations that have happened in the last, it's 2010, so in the last 30 years to Ruby, right? So those are things like optimized machine code, bytecode virtual machine, sophisticated garbage collection, all those things that computer science people have been working on. How can we bring those to Ruby? That's always been the aim. Just a quick example of something that we really pride ourselves on is bringing these things in and making them available to Ruby in a way that you guys don't even really have to do anything. You just sort of get them for free. That's the idea of being drop-in compatible. So this is just a quick example. So normally in Ruby, when you've got an object that's got instance variables, so we all know that you don't have to declare your instance variables in Ruby. You can just use whatever ones you want, and they just sort of appear on that object, right? In fact, you can even add instance variables in methods that were mixed in, and they still all sort of work the way that you would expect. So consequently, in Ruby, normally your instance variables are implemented sort of like this. It's basically just with a hash. We've got the keys and the values. It's sort of what you would expect from just a simple implementation of this. You don't know what the keys are going to be in the future, so you just want to live it up to some kind of implementation that lets you add arbitrary keys in there. The problem is that now if I have 1,000 one of these obs, right, 1,000 instances, now I have 1,000 hash tables, even though, and all of them redundantly have a key with name that points to some value and a key with age that points to some value, but those keys are all redundant, all the same, all the hash tables are the same. So we set out to really, because we implement so much in Ruby, we needed to figure out how can we get our memory usage down. So because we have so many Ruby objects, if we improve the memory usage, we improve it just sort of out of the box, memory usage would go down. So what we do is we come up with a technique that lets us turn it from this into something more like this. So now what we've got is the ability to have the instance variables that are just sort of an array, and then you get this shared hash that is shared on the class. And now, instead of 1,000 one of these hashes, you've got one of them. And instead of 1,000 hashes, so instead of 1,000 hashes here, you've just got one array that maps these values here to the numbers here. By and large, this ends up having a huge memory efficiency improvement. And what we can do, because we do so much of the processing in Ruby, because we've got a really nice sophisticated VM to do these kind of things, what we can do is just spy on all the instance variables that a class might be using, and just add those to this hash, just one after another. So you don't even have to do anything to improve the memory usage of your program. You just have to sort of write Ruby in a very normal way, and our system can actually figure out the best way to lay these things out in memory. So just to sort of to emphasize the point lastly, this is actually what it ends up being inside Rubinius. It's not actually a separate array. We get this nice, very simple, compact representation of the object with the actual values stored right there. And this had actually a really big, I think we went from something like 120 megs in a very simple case down to something like 80 megs. So again, that was a really big improvement just with this one simple little thing. This is just a quickie example of the kind of things that we try and do every single day, that we try and bring to the system to really keep building a better VM, keep building it up, but something that you get for free. So one thing that we try to emphasize a lot is that we want to be friendly to developers. If I'm selling something, I'm selling it to other developers. So it's really about developers. Developers, 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 developers. And what do developers love most is they love APIs. They love being able to poke and to twiddle and to fiddle with things. So really what we try and do is we build our tools around APIs as much as we can. We actually, if we want to build a tool, we build an API for that first, and then we build a tool on top of it. Even if the API is kind of crufty, even if it is kind of weird, we build some level of version 0 API that we can build on, that people can use, that we can get feedback on, and we can move from there. Because that allows our users to build more, because they can use those APIs, they can extend, they can take it sort of to the next level that we couldn't do with those tools. So a really great example of something that is very rarely an API is our compiler, our bytecode compiler. It's a full, just normal API driven. And originally, we didn't set out necessarily to make an API. It turned out that this was the easiest way to do it, but it's become really important. And we got a double slide in there. But so really, the example of this is there's a language called Fancy, which was presented at OSCON. It's kind of just a language that a couple of guys thought it'd be fun to write. It's different than Ruby. It's actually more small talkish than Ruby, and they try just sort of experiment, as we can all do, just experiment with something new. But because Rubinius had its bytecode compiler all API driven, it provided them the ability to just write their language directly to running on top of Rubinius bytecode, because they can reuse our compiler. They don't have to go through and rewrite all of that logic to figure out how to write the compiler. They can simply write to our API to generate those kinds of really interesting applications that personally we don't have time to come up with. But because we're writing those APIs, people can do it for us. So that's all nice and good, but if Rubinius is a drop-in, then why should you even bother to use Rubinius, right? If it just drops in, it's exactly the same as the things you had before. Then what's the catch? What's the big deal? Why should you spend the time to try and do that? So what we're going to talk about, okay, these slides do not go the way I thought they did, but that's okay. So because we focus on developers, and because we are really Ruby developers, we sit every day and we're working on Ruby code. And occasionally we work on the, like C++ or other languages to get what we can't do in Ruby. But by and large, every day we sit there and we're writing Ruby code. And so we have had a lot of experience as Ruby developers writing essentially a very large Ruby program. And because we've got control of the whole system, we've got a lot of tools that were born from that need. So from those 2 points of why should you use Rubinius to this idea of tooling, we've actually built a lot of interesting tools that can help you solve sort of day-to-day problems that you have got. So what we're going to go over in this next session is really these 3 simple problems that pretty much every Ruby programmer runs into, and how Rubinius can help you solve those specific problems. So the first one is improving an algorithm. So who here has ever gotten code from a coworker that you didn't like, and you were told to improve it? Raise your hand. If your hand is not up, then you should give one of these other people with their hand up a hug. Because the reality is, it's always extremely painful. It can be extremely painful. And when you're told to not just, say, fix a bug on it, but to actually improve it, that makes it even more difficult. So let's look at some tools that Rubinius gives you to help do that. So the first step of trying to improve an algorithm is always to benchmark. You should never start off trying to improve something, we're talking improve performance-wise, improve something performance-wise without benchmarking it first. So you write a real simple benchmark script that looks something like this. You've got your coworker's code, and you know that you need to be making calculate awesome score faster, right? But you don't know what faster is yet because you don't know what the speed is right now. So you go ahead and write this to calculate that out. And you get some output that looks like this. And really, what everyone in here did is they looked at this rightmost number. Probably very few people even looked at these other 3 numbers. And so we're going to take a minor tangent, and we're going to talk about this output. Because this output will inform us, not just this rightmost number, but the rest of them in how we figure out what our solution is. So, like I said, we looked at this rightmost number. Let's go back to here. Let's break it out into a slide that's a little easier to see. So, user is really low, but user's low, system is super low. This total looks like it's the addition of these, and then real is massive. So what are these individual columns mean? Well, user is the time that your program spent running user code. So in other words, the time running loops, the time doing calculations, all that kind of stuff. System is the time inside the kernel. So if you go out to do I/O, that's where you're actually asking the kernel to perform some operation for you. So your user time stops and system time starts. So it'd be obvious, therefore, that the total is going to be the sum of those 2 things. And the real on the end there is the elapsed wall clock time. So what is wall clock? Now that would be the time you would measure on a stopwatch. So if when you hit enter, you were to start a stopwatch, and if it finished, you were to finish the stopwatch, that is what the time would say. And that's why generally people look at this bottom number, because that's the one that the human experienced. You running this thing experienced the real number, the wall clock time. But what you should be asking yourself is, why does the total not equal the real? Because if the only places to spend time were in the system, in the user, and in the system time, then why are these not equal? And we'll get back to this in a sec, but knowing why this is a little later on as I explain it will help you figure these things out in the future. So we've benchmarked it now. We go on to step 2, you just need to profile it. So you know it's taking basically almost 30 seconds to perform this one operation. So where is this time going? So Rubinius gives you a built-in profiler that's wired straight into the VM that gives you instrumented profiling results that you always have available to you. So you can just run, so again, what we've done is we've run the program. This time we've dash capital X profile. So generally what we do for Rubinius is we have these dash capital X options are sort of internal options, so they won't collide with the normal Ruby options. So in this case, we'd say turn on the profiler. And so we get some output that looks like this. We run just our sample here. And we see, okay, well, this is not very useful. This is probably what you would say. You'd be like, if you only stopped here, you might write me an email saying like, Evan, your shit sucks. I ran this benchmark, bro, and look, I'm getting 99%. I just can't use Rubinius anymore. You close up your laptop and maybe you go back to your work, which is sad. Because you need to go a little bit further. You need to figure out why is this, whatever this is, receive timeout, why is this taking up this much time? You can't stop here. You have to go to the next level. Oh, I bamboozled my slides. That's okay. So what we do is we run it again, but this time we pass in an extra option. We pass in this -x. I'm not going to bamboozle this set though. -x profiler.graph, right? So this will give us, this will tell the profiler that we want more information about what happened. We don't want just this very simple, like, this took up a lot of time, this didn't take up any time. That's just an oversimplistic view of figuring out. We want to know, where is this time going? So profiler graph gives us the ability to figure that out. So now we're going to get a whole truckload of information, probably about 40 times more information out of profiler graph than we got out of the last one. So it's going to be a lot of data, right? But before we knew, remember, we knew that it was this thing called receive timeout was where we had the most things. So in this big truckload of data, what we do is we find a line for receive timeout here. And I'll give you the quickest possible intro to this format is that, see how this is indented more to the left than the thing up above it? The line that is indented to the left is the primary entry. So what this is saying is that kernel sleep called receive timeout, and it called it 10 times, and it took up 30 seconds for 99.9%. So now we're on to something. So we've seen inside, what we're seeing here is how kernel sleep is implemented. It's implemented with this thing. You don't need to worry about it, but you know, okay, sleep is the bomb diggity. That's what we need to be checking a look at. So what you do is you say, okay, where's the entry for sleep? And now you get this entry for sleep. You correlate them by saying this call entry for sleep. Now we look at the primary entry for sleep. And so we have it right here. And now we're getting somewhere. Oh, look at this. We've got some coworkers code. We got something called superhero factor. Well, what is that action? We got it. Now we're inside the coworkers code. Now we have a place to actually start looking at the code. So we go ahead and we find that method, and we open it up, and we find this. And you probably want to shoot them, right? But now you've figured it out. You didn't have to go trucking through all their code one method at a time to try and find this. You were actually able to pinpoint it. So now we're on to step 3. You take that line out, you fix it. In this case, you take that line out and you fire the guy. But right, so you fix the problem, right? So now you benchmark it again, and now the lines. Now everything is looking great. Right? Now you get to go home, right? Now it's maybe a Thursday. You take a Friday off, boy. Oh, yeah. So let's go back to our little mystery from before. Remember this guy? I'm sure you've all sort of figured out what it is, which is that sleeping is invisible to all but real time. So if in the course of looking at your profiler results, you see a total that is wildly different than your real, you've got really only 2 reasons that can be. One, your coworker is fucking with you and has put asleep in a method called superhero factor, and then you want to get on the phone, right? Probably call somebody about that. Or number 2, you're on your server that is running this program is heavily loaded down. So what that actually means is that the time, so your elapsed clock time was click, blah, 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 click, right? But your computer was emulating multiprocessing by swapping processes in and out. So if you had a very heavily loaded down machine, even if your code was simplistic and it just had an algorithm that could run very quickly from front to back, if the kernel was so busy with everything else in the system, it couldn't get around to actually running your program, you see a massive skew between your real time and your total time. So that's a really good way, actually, to figure out if you're running on a server that is having really hard problems keeping up with the kind of workload that you're trying to throw at it. So that's sort of a bonus to knowing how those benchmark numbers work. So improving an algorithm, solved. Go home. Take Friday off. You deserve it. So let's go on to the next one. Who here has ever had a slow or hung Ruby process? There we are. We'll leave that for later. So what we've got inside Rubinius is the ability to, we have got a specific functionality called the query agent that lets us figure out and ask questions of Ruby processes. So let's see a little bit how that works. So here we've got just some random, whatever it is, I don't know what it is. It's just some server, and in this case, it happens to print out the time it started on, it said it started, and it's PID. So it's just a server that's doing some normal servery thing, but it's totally hung up. So what we want to do is we want to use query agent to inspect what's going on. So what we do is we start it up again, but in this case, we've actually added this -x agent start option. So we've actually told the system, oh yeah, by the way, go ahead and start the query agent. There's no overhead for doing this, so ideally, we've talked about basically doing this on every process because it's really sort of a no overhead. There's nothing, you wouldn't pay anything for this. But ideally, on all your server processes, you would be doing this so that you could, when you run into the scenario, you can fix it. So what we do is we've built in, the query agent is built in, we've also built in a thing called just a simple console that can talk to other processes running query agent to figure out what they're doing. So in this case, what we've done is we've opened up another terminal on the same machine, and we've run RBX console. And in this case, what it actually did was it figured out, oh, look at this. There's actually another VM already running on this machine, and it was connected to this port, whatever, just some random port. And it automatically connected to it. So it does this because it sees, okay, there's only one other Rubinius there. That's the one you wanted to connect to. And you can verify that by running the PID, and you can see that that's the same PID as we had over here. So you know, okay, I'm connected to my server now. And then what you can do is you can just say backtrace, and you get this large backtrace. Let's bounce it up a little bit here. So in this case, what we've actually asked for is a hung process. We have now remotely retrieved a backtrace of exactly what every single thread is doing. In this case, it's only one thread. And now what we can do is just look through this backtrace to figure out why is that hung? What is it doing right now that is causing it to A, be slow, or B, be completely just stuck? In this case, we actually just want to look at these top few lines, because we can see that most of this is just sort of Rubinius intro code trying to load in that script. In this case, okay, we've got this important server, it's getting a request, and then we're doing oh, look at this. Maybe it's stuck inside some I/O requests. So this backtrace is, because we've got so much inside Ruby, written inside Ruby, these backtraces can be very detailed. And they'll give you, they can tell you exactly what's going on. In this case, we can see that we're actually trying to fill some I/O buffers for getting some output. So our process is hung just waiting on some I/O. So additionally, what you can do is you can use this query agent protocol to just do now you could it's running slow, so it's maybe running in spurts. It's only running at 5 requests per second instead of, I don't know, 5,000. You want to figure out why that is. You can easily script that to get many backtraces and then sort of compare them over time and get a snapshot of what your process is doing as it progresses over time. So what we've done is we've added an extra option here that will output these lines right here, these query QA lines that give you a little information about what the query agent is doing. In this case, now what we can do is we can do another option to console. What we said is actually connect to that specific port. So we did verbose, it gave us the port number. So now we can say, okay, connect to that port and give us a backtrace. And now we get the backtrace and it exits. So now you can actually script this. You can give this to your system administrators and you can say okay, if you've got slow processes, this is the tool you can use. Run this thing, it'll grab, say, 30 backtraces over the course of 30 seconds and use those to try and figure out why is it slow, what kind of information can I give to the developers to try and fix this specific problem. Additionally, like I said earlier, we're focused on how can we build tooling to make these things better. So console is actually the sort of sample, the simplest possible interface to the API that